Welcome to the first of the pre-lab video series for Organic Chemistry Lab, um, CHE211, and this is going to be your first, as we would call it, a wet lab experiment or a lab because we're going to actually be doing a real organic chemistry experiment in the lab. So I hope you're excited about that, and it's really important that you watch these videos ahead of time before you walk into the lab, so that you're actually prepared and know what to do and be able to finish your experimentation within the allocated time for the lab class. And if you do this well, you should be able to finish writing your lab notebook entries within the allocated lab time as well. So, um, what are we doing here today? Well, we are going to be, or I should say, on the day that you're going to be doing your lab, hopefully this is like maybe a day, at least a day before your actual lab, and not like 10 minutes before the lab period, because you're going to have to turn in your pre-lab at the beginning of the lab, and that cannot be late. All right, so yeah. um, what are we doing here? Well, we're going to be identifying some unknown drugs by an organic chemistry technique called thin layer chromatography, or TLC, and that's something that you're going to be using a lot, especially actually next semester when you work on a synthesis project where you'll have your own target molecule that you get to pick that you will want to synthesize from scratch. And in the course of that synthesis project, you'll be analyzing your reactions, excuse me, and your reaction products a lot by TLC. So, what's at stake here today is to determine what drug components you have in your unknown drug pill. Now, it can be one of the following. It's the components in your unknown drugs could be aspirin or acetylsalicylic acid. That's a little more of a chemical name. Aspirin is more of a commercial name. Or acetaminophen, or ibuprofen, or caffeine. So the ingredients for your painkiller drug, unknown drug, can be one of those four things. Sorry, I'm not showing the structure of caffeine here, but um, that's going to be part of your pre-lab prep, is to look for you to look up the structure for caffeine. And knowing the structure is important because that will tell you how polar each of these compounds is with respect to each other, and that relative polarity will tell you how far they will move up, um, or how far up they will move on the TLC plate, as you'll see later. Now, let's imagine a situation where you have this horrible syndrome or disease called Stevens-Johnson syndrome. Now, that could manifest itself in a number of different ways, but one way that it could manifest itself is that you could be severely allergic to ibuprofen, and if you have this condition. Um, there was this one child, I believe he was from the UK, that his mother did not know he had Stevens-Johnson syndrome, but his mother gave him ibuprofen when he had a cold, and to lower the fever and whatnot. And it turns out this child had Stevens-Johnson syndrome, and I know this is a little bit on the graphic side, and I apologize for that, but he suffered this horrible consequence as a result of taking ibuprofen, because that's the result. Now, let's imagine that you or your loved one has this condition now, and you're not 100% sure that this particular painkiller pill that you have in hand does not contain ibuprofen. You, as an organic chemistry student, how could you possibly figure that out? How can you determine whether or not this particular unknown drug pill tablet does contain ibuprofen or not, and thin layer chromatography, or TLC, will enable you to do just that. And we'll talk about how that works next. We want to analyze the unknown compounds and see what, identify them to see what they are using TLC technique, or thin layer chromatography technique today. And what we want to do first is to obtain a TLC plate. Now, it should have, TLC plates usually come in a 20 centimeters by 20 centimeter square, but that should have been cut into 4 strips of 20 centimeter length and 5 centimeter width for you. If not, let me or the lab assistant know. And what you want to do then is to take a really good pair of scissors, because if you use a really bad scissors that are not very sharp, you're going to get a really jagged edge of silica gel, and that's not going to work very well. I kind of got ahead of myself. TLC plate is made, the kind that you're using will be made of either plastic backing in the back or aluminum backing, but most likely plastic. And so it's really just a plate of plastic, but on top of that is a coating of silica gel, which we'll talk about what silica gel does in a second, but this is what TLC plate looks like. And so what I did here is to take this strip and carefully cut it with a pair of scissors, so that I have just a TLC plate that's 5 centimeters high. This comes from 5 centimeters width, and a few centimeter wide of a TLC plate. So 5, a few centimeters width. Okay. So let's talk about what silica gel does for us. So that's the material that is on the TLC plate. And silica gel at the molecular atomic level, it looks like this. The main thing I want you to know about this molecular structure is that, well, if you know anything about glass, that this is actually glass, and silica gel really is just ground up powderized glass. That's really what it is. And on the surface, though, you have silicon oxygen bonded to a hydrogen bond, and this is a highly polar bond, as you can imagine, because of the electronegativity difference between oxygen and hydrogen. This is a very polar bond between oxygen and hydrogen. So there's going to be a substantial amount of partial positive charge on hydrogen, partial negative charge on oxygen. All that to say, the surface of silica gel is extremely polar. Okay. So as you can imagine, any compound that has inherent polarity to them, so polar compounds that possess dipolar polarity, like say if we have something like, let's say, acetone. Well, this has a polarity to the molecule. The oxygen is a lot more electronegative than carbon, so there's a partial negative charge, partial positive charge there in this molecule acetone. And what happens is, because this is polar, when a polar compound comes in contact with silica gel, there's going to be an attraction between the two. They will I'll probably keep using the word interact. They'll interact with each other a lot. That means that those polar molecules will move slowly, going past silica gel molecules. And that's the key, is how fast something can move past silica gel. That's sort of the key concept in chromatography. And because the silica gel is fixed onto this plate, we would call the silica gel stationary phase. this is the stationary phase that we're using in the chromatography. Now, that does imply that there's something that's going to be mobile, and there's going to be a mobile phase. Only I can spell that word. Mobile phase is going to be the solvent that you're going to be selecting and using to run the TLC plate. And what's going to happen is you'll dip the bottom of this TLC plate. Remember, this white stuff is the silica gel, right? Silica gel stays in place, and the mobile phase is going to be the solvent molecules. Because of capillary action, when you dip the bottom of this TLC plate, the solvent molecules will go up the plate, and you'll be able to visually see that. And I'll show it to you in a minute. And mobile phase, or the solvent, is going to carry the analyte or the sample that you're analyzing along with it towards the top of the TLC plate. Now what happens is, if your analyte is polar, then because it interacts with silica gel quite a bit, it moves up the TLC plate rather slowly. But if your analyte, the sample that you're analyzing, is not as polar, then it's not going to interact with silica gel. So what happens is those molecules will then move up the TLC plate rather fast. Now, as far as how to prep the TLC plate, you will want to, with your pencils, mark some dots. How many dots, you would ask? That's how many samples you're comparing on the TLC plate. So if you're comparing just 2 samples, you will want to put 3 dots. So I guess I should have said that's how many samples you're comparing plus 1. So let's say in this case we're just comparing sample A and sample B, and we're going to also have a mixture lane. Maybe I'll put that in the middle. And let's say that A is a relatively speaking non-polar compound, and then B is relatively speaking a little more polar than sample A, let's say. And what you will do is to take a small capillary. I don't know if you can see this on the video, but this is a capillary that I made from stretching a glass Pasteur pipette using flame. And I'll actually, it'll look like that. Here's a glass Pasteur pipette that was stretched or melted first by flame and then made into a capillary. I'll show you how to do that in a minute also. But using this capillary, you will want to dot sample solution. And now you need to make a solution first, as the manual suggests. Dot some sample solution onto the or spot sample onto the dot that you made with pencil. It really needs to be a pencil. If you use a pen, that ink is going to actually dissolve in the organic mobile phase solvent, and that will actually very much confuse your results. Okay. And here what we're doing is I would then dot or spot sample solution A onto this dot and also onto the mixture dot. And then I would clean the inside of the capillary with some acetone. And to do that, you can just dip the tip of your capillary into acetone, maybe taken in a little beaker, and then you can spot out that acetone solvent that's taken up in the capillary onto, say, a paper towel or a Kim wipe, and then that will sufficiently clean the capillary. And you might actually want to do that about twice to ensure that the inside of the capillary is clean, to avoid any cross-contamination. And then you will take a sample of solution B and dot it on the dot B, as well as the mixture dot. Now, what will happen, remember that A is more nonpolar than B. Once you dip this TLC plate in TLC developing chamber. This would be the TLC developing chamber. I don't know if you can see there's actually a solvent at the bottom. You really don't want to use more than 3 to 4 milliliters total of the mobile phase solvent. Okay, and then you will want to carefully, using a pair of scissors, you will want to carefully place the TLC plate into the TLC developing chamber, like so that it actually leans against the wall. And as soon as you do that, you will want to carefully put the lid back on. And now the reason for that is that the inside of this TLC chamber needs to be saturated with the solvent vapor. Otherwise, what's going to happen is the rate of evaporation is going to actually change how fast things move up and down, and it'll complicate the matter. And the how far the analytes travel, which is called the RF value, retention factor value, that's going to vary every time you do the experiment. And so to keep it consistent, you need to have a lid on. And now I don't know if you can see on the video, but you can actually visually see that the solvent is moving up the TLC plate. And when I place this TLC plate in there, it's actually really important that the place the dots that you spotted your samples, they need to be above the solvent line. So this is your mobile phase solvent surface. They need to be above. If they're immersed in the solvent, what happens is the samples will just dissolve into the solvent and they will not go up the TLC plate, and you will get a really awful TLC development or developed. So make sure that the dots are above the solvent, and after a few minutes, what happens is solvent will run up the TLC plate, and after it reaches within say maybe about 4 millimeters or 4 to 5 millimeters or so from the top, when the solvent reaches that high, we're getting there with this TLC plate. You will want to take the TLC plate out and immediately draw a line with a pencil where the solvent line reached. So it's slightly premature, but just for the sake of time, let me take this TLC plate out carefully again with tweezers. And then before the solvent dries, I just drew a line on the top signifying where the solvent reached to on the top. So that's the solvent line. Okay. Now I didn't have the A, M, and B written on the TLC plate a second ago, but that's because I'm just doing a mock run with nothing on it. Now, once the solvent reaches to the desired height on your TLC plate, and you've already drawn the solvent line, what you will find is that these compounds have moved up on the TLC plate if you have chosen the mobile phase solvents wisely, and we'll get to that in a minute. But the problem is these compounds are not colored, meaning you cannot see them on the TLC plate, but they are there. So to visualize them, what we're going to do is to put this TLC plate under a UV light. And the reason why that's going to be helpful is this TLC silica gel is actually mixed with a fluorescent dye, and so when you shine UV light, specifically 254 nanometer UV light onto this TLC plate, those fluorescent dye will fluoresce, and you will see this glowing, beautiful green, yellow-green color. Now, if there's any compound that's present on the TLC plate that absorbs any UV light at all, and a lot of organic compounds do, that part of the TLC plate will not fluoresce, meaning that the part of the TLC plate that has a compound on it or analyte on it will appear dark under the UV lamp. And so, and for an example of that, I think you can see a picture of the example under UV light in the lab manual. And so, let's say that here's our dark spot. Okay, for A, and then maybe this would be the dark. Ideally, we don't want it to be that big, the spot. We want it to be actually small. And when you spot your sample on the TLC plate, you will actually want it to make it so that it spots as small as possible. So a trick to do that is you spot your sample a little bit and let it dry, and spot more of the solution and let it dry, and you keep doing that. That'll make the sample circle rather small. Now this is what it would look like if we were to spot these two analytes on the TLC plate. So what we are showing here is the sample A, remember, is non-polar, so it travels faster because it doesn't interact with silica gel as much, where sample B is polar. It interacts with silica gel quite a bit, which slows down its traveling time, and so it doesn't travel as far on the TLC plate. In the mixture lane, you've got both A and B present in the same lane. Now, and then here we can see a good separation of the two samples. And now if you have another lane over here, if we had another lane for unknown, and let's say the unknown sample traveled to this height, then you would know that that unknown sample, its identity must be A, sample A, rather than B, because it traveled as much as A did. And that's how we would use TLC to identify compounds. Then we'll talk about how to choose your mobile phase solvents wisely. And the key idea here is that you want the solvent or mobile phase to be, its polarity to be just right, so that your analytes will travel to about middle of the TLC plate. And to talk about where the sample spot appears on the TLC plate, it might be good to talk about the RF value, which is already defined for you in the lab manual. But you will want to take the distance that the solvent traveled from the origin sample dot. So you will actually want to take a ruler, and let's say that this distance comes out to be 4.5 centimeters. And then let's say that your sample B traveled, and then you will want to take the middle of this dark spot for B, not the top or the bottom, middle, and you will want to begin measuring from the sample dot for B. Let's say that this distance is 1.8 centimeters. Then the RF for B, sample B, is going to be 1.8 centimeters divided by how far the solvent traveled, which is going to be 0.40. And because it's a ratio, RF value actually doesn't have a unit. And so that's how you would calculate RF. And typically you want the RF of your analytes to be anywhere between 0.2 to 0.8. Anything higher or lower than that means that your sample moved way too fast or way too slow, and it's hard, at that point it's really hard to compare when your RF is only like 0.1 or when your RF is almost 1, like 0.9 or something like that. So you will want to choose your solvents such that your analytes appear sort of in the middle of the TLC after you run them. Okay. So to do that, we have some choices for the solvents or the mobile phases, and you have some choices because I want you to actually, through trial and error, aka through experimentation, like a scientist, because in organic chemistry, one of the goals in the course is for you to start to develop as a scientist, and to be a scientist, you'll need to be able to, through experimentation, determine something that was not previously known. Like in this case, what would be the ideal mobile phase choice? That is not spelled out for you in the lab manual, so that is not known to you, and I want you to have an opportunity to figure that out through experimentation. And so, I'll give you some tips. Usually, it's easier to pick one solvent from the non-polar group and another solvent from the polar group that are miscible with each other. Now, you have to be careful with that because, for example, hexane and methanol will not be miscible. I guess I pointed to water, but hexane is not miscible with water either. So, whereas hexane and ethyl acetate, those two are miscible, or hexane and diethyl ether, those two are miscible with each other, or cyclohexane and diethyl ether, those are miscible with each other, and so forth. Methanol and dichloromethane are miscible, so those are good combination and combination examples. The reason why combination of mobile phases is convenient is because let's say that when you run your TLC plate, your RF values turned out to be just a little too high. That means your mobile phase is actually too polar, because if you think about it, if your mobile phase solvent is very polar, what happens is all the silica gel molecules on the TLC plate will be busy interacting with your mobile phase solvents, and they will not have time, so to speak, for interacting with your analyte. So when you have a polar mobile phase, your analyte actually ends up traveling a lot faster. Let's say in this case, let's say it travels way too fast. And in that instance, you will want to actually decrease, because you can't do anything about the analyte, your sample. You can't change that, but you can change the mobile phase. So if this happens to you, if things move too fast, you will want to decrease the polarity of your mobile phase. And if you're using a combination of nonpolar and polar solvents, that'll be easy to do because you just have to decrease the ratio of polar solvent in your mobile phase mixture. So for example, if you're using hexane and say ethyl acetate, and let's say that ratio was hexane to, this is abbreviation for ethyl acetate, let's say this was 4 to 2 to 1. And let's say that turned out to be too polar because all your analytes traveled way too fast, and all the RF values ended up to be like 0.9 or higher, be too high. Then what you can do is to adjust the ratio to something like 5 to 1 or something like that, and that way it would have a lower proportion of polar component of the mobile phase mixture. So then things will slow down and your analyte won't travel as fast in that instance. Okay, so that's how you will pick your mobile phase. Now, when you're picking your mobile phase, it may be easier if you first just try spotting just the known standards like ibuprofen, acetaminophen, aspirin, caffeine, and so forth. And make sure to label the origin points or the dots for spotting of your sample solutions. Now, you might want to just do this with your known standards first to figure out what would be the good mobile phase combination for you, and then presumably the unknown sample is going to have one of these known samples, and so you could then apply that mobile phase for a TLC plate that contains not only the known standards but also your unknown, and then don't forget to have a mixture lane. Now I wrote the mixture lane right here on the edge, but you will not want to have a spot really close to the edge. Edges of TLC plates tend to be jagged, will tend to have a jagged edge, and because of that, that sort of messes up with the capillary action, and so solvent tends to move a little faster on the edge like this. So solvent actually tends to move like that in a concave fashion. So you will not want to have a spot too close to the end or edge of the TLC plate. And also you want to be careful with having the spots too close to each other. So you will want to have plenty of space in between sample spots on the TLC plate. Here's how you can make a capillary from, I don't know if you can see this, but a glass pasture pipette, which is made of borosilicate. This can melt at a higher temperature, which we can achieve with this handy dandy Bunsen burner, which I'm hoping you have had a chance to use one in your general chemistry course. But if you haven't, just to give you a rundown on this, a brief one, there's two things you can adjust for a Bunsen burner: the airflow and the gas flow, because you need those two things to make a flame. And when you light a Bunsen burner, you will want to actually have a low airflow, because if you have too much airflow, the gas comes up way too fast and it's really difficult to light it. And then you can adjust the gas flow with this dial in the bottom. And so what you will do is first turn on the main gas, so right here, and you might be able to hear the hissing sound, but now gas is coming out of the Bunsen burner. So, and I've just lit it. I don't know if you can see that, the blue flame. And now that it's lit, you can open the air gate fully so that it's getting enough oxygen to combust at a really high temperature. And now when you do this, you will actually not want to wear gloves, because just I'm praying you won't get burned, but if you get burned on your hand with a flame, you will not want to have a glove on you, because then the glove material will melt into your skin, and that's going to be worse than just getting a burn. So hold your pipette like so, and you will want to heat this part of the pasture pipette, so this part, okay, like I'm doing now. And what you will notice is in a look, I don't know if you can see it on the camera, but in a second, after a few seconds of doing this, you'll begin to see the orange flame, and you will begin to see the glass, the pipette itself will begin to sort of glow a little bit, and then you will actually, you can only go by the feeling, but it's gonna feel really soft. And then you want to pull the pipette out of the flame first, and then pull it really fast. Now be careful, because this this glass is still hot from the flame. Okay, so you can set this down on the black bench top, but otherwise do not touch it. That's how you can get burned doing this. Now I don't know if you can see, we made this really nice capillary. As far as the desired diameter for this, it's really hard to explain on the camera, so you can ask your instructor, I guess like me. But after you make this capillary, it's easy to break it off with your fingers. And so and now it doesn't need to be this long of a capillary, but now I've made enough for quite a bit of experiment, because these things tend to break. Now when you make the capillary though, with using your finger, you will want to make sure that the end of the capillary is broken in such a way that it's really flat, because if it has a sort of slanted angle, it's really difficult to spot your sample solution onto the TLC plate. It needs to be flat for the solution to come out onto the TLC plate. So this is how you make your capillary. Be careful with the flame, please.